You don't know, okay.
It does say on the first line your initial argument. I mean, if that's gonna be another word for my claim that I can go here, then I'll go before the other.
So what was your initial argument?
See the blank face we're all going,
I mean,
our initial argument was that very general that the liquids would settle according to their mass by volume. Yes,
okay,
that was, we did not go very specific, this will go here, this will go here, this will go here.
okay. That's, and did your claim, did you prove that, or did you support that with your evidence?
Well, yeah, our claim is general in that they fall by mass. Oh wait, no, it didn't back up. It is.
Our evidence didn't support. Why do you think your evidence didn't support your claim?
Human error.
Inaccuracy in measurement.
So you're not saying your claim is wrong, you're saying I did something.
Or, and as she said as well, in our measuring tools, being in gradients of 20
Yeah.
makes it very hard for us to make sure that they were accurate.
And the residue that was left in the Dixie cup reported and all
Yeah.
that.
Okay, that's a good point. Anybody else? Nothing? Got nothing? Candace?
This discussion, I heard a lot of accuracy and precision. Which came back to, well, I mean, I can't speak for other people's group, but our group, we went through and held the volume the same for each substance, and then measured the masses. And based on the data from our calculations did not coincide with what we actually observed happen. So I heard lots of discussions about precision and accuracy. So maybe, I always forget this, so maybe we could have that discussion.
So I don't know if it was your group that had a Y circle on the poster. I thought that was awesome because there's your next testable question. Why did that happen? What could we do to see if that would happen again? But I really like that. That was really, really a good thing because that's where the kids would want to go next, right? So, and I was just thinking, how would you test that? But then this group said, we had residue left in our cups, our measurement, our beakers were not real, what's the word I'm looking for?
Accurate.
So.
My question is, the main part that I think went really well for us is we measured 4 centimeters on the Dixie cup, and then you measured it out, and you took the mass of an empty Dixie cup and subtracted from that. But once you determine the mass of the substance in equal amounts, does it really matter though once you're pouring it in? So I don't think that part.
I didn't, yeah.
I could be mistaken, but I think what they're saying is they measured it this way and then they dumped it into the Dixie cup.
No, that won't
Not
matter as
dumping it
far
into
as the,
Oh, okay.
that won't matter as far as the visual element of the container. That, the problems that we had were in probably the measurement tools, because the expectation, we were just talking about this outside, is for water to be right at 1 milliliter per cube. But ours was not, ours was almost a gram off.
Right.
So
Okay.
there was a problem somewhere along the way.
Measuring the mass using the same amount of volume.
So Ashley, what I think, just let me confirm what I think I heard. Y'all did not actually, y'all didn't calculate anything.
No.
You just took equal volumes
Right.
relatively.
Right.
You just marked your cups,
Mm-hmm.
filled them up to the same level,
We got 6 of
and
them.
then measured the mass. Okay, and then what did you do with that information?
We use that to try to make our claim of which one would be, the most dense relative to the others. And from greatest to least
Okay,
for our claim.
okay. Did anybody else do it without calculating anything? You did? What did y'all do? Well, yeah, y'all did
Our
something very
group, we
special.
didn't have a scale, so we put everything in the cups and we kind of just measured, this one feels heavier than this one. And then we lined them up based on what we thought, how they would end up in the jar, in the glass. But then, so we started thinking, okay, well, we started thinking of an oil slick. Whenever they spill oil in the ocean, the oil's on top of the water, so we knew, so then we started switching the cups around. And then you use alcohol to get water out of a gas tank, so the alcohol would have to be on top of the water, so then we switched those. And then, so we had them all lined up on how we thought they would end up in the glass. And I think we messed up on one or something.
So
And I
when-
did not realize the alcohol would split like that.
So whenever you were doing your relative masses, were there any that were, I mean, you had, what, 5 liquids? How hard was it to hand compare them, their
Well, the
masses?
soap and the oil was obviously the heaviest. Once we got to the water and the alcohol, that's when it started getting, that's when we started thinking, okay, alcohol in a gas tank, so that's how we
Okay.
kind of started.
So you used your observations for some of it and then relied on your prior knowledge for other parts? Okay, okay. Anybody else not calculate anything? Quentin? Did you want to share?
We took the measurements, but we didn't calculate
Okay.
we didn't know if we were supposed to or not. But we used the same volume, 60 milliliters across the board, or as close to as we could measure.
Okay,
And then we weighed it. And it didn't match up for us either.
so what could we do different in the future when we're doing this? I mean, how could we improve and make this better?
I think we could talk, generally speaking, about just basic density or buoyancy, but density, how you can have the same amount of, or volume of, let's say, feathers as compared to lead. And you would see a difference of mass there, so you just, depending on what grade level you're talking about, you can, make these differences, how some things are more dense as compared to other objects. What does that mean when it's more dense?
So if the purpose of this was an engage, because I purposefully
Right.
did not write density anywhere on there. I didn't say the word density. So, I mean, are you saying you would have benefited more from hearing that word ahead of time?
I don't think we'd have to actually use the word depending on the grade level, but you could show that you stuffed in styrofoam. And then you could have water, and you could ask them, what do you notice? This has the same amount in this container as well as this. What do you notice about these without ever using a triple beam balance? What do you notice about this? Okay, and then we get something else, and they start comparing. And then if you say, okay, now, if I were to put this in a, column, I have to find what a column is, or, depending on the grade level. Where do you think that these would be in relationship to one another? As in a liquid form, or
Okay.
as some type of liquid.
Okay, all right. Well, we're actually gonna do a lot of that tomorrow and make those observations. So thank you for sharing that. Dr. West, did you want to?
I was multitasking, but I'm ready. Okay, specifically for this one, Laura and I had some interesting conversation about this. Laura, you want to tell them the background on where this lab came from?
Yeah, this was something that my district, the new thing is ADI, argument-driven inquiry. And the the background is that the research shows that if you struggle with something and have to work through that concept to figure it out yourself, that you learn it better long-term than if you are just, these substances are going to, layer according to their densities, and we're done. I could have told you what would have happened in one sentence, and then we move on. But you don't know that experience. You haven't had that experience. So the research shows that when you experience it, you don't know that concrete stuff. You remember this. Okay, so I went to a several-day training where we wrote these investigations, and this is one that we wrote earlier. So
But you and I kind of rewrote it.
yes, we did rewrite that because a lot of that comes with the background information that gives you the answers before you have time before you have the experience to understand it. So it would have been like me saying, this is how it's going to work. Now you do that and tell me why it's going to work.
The old cookbook lab is what they've typically been called. And in the ADI training, they gave the background information, which if you handed that to the student, is gonna give them the answer. Therefore, they're not going to struggle through it like Laura's talking about. The irony of this is that this person who's doing this group is doing this, is making a lot of money. The way that you're being asked to write these up are the same way that we have been told to write up labs for decades. This is not new. This is the way it should have been done all these years. But I think what this brings back to the forefront is how students need to struggle. And y'all asked tremendous questions out there. I mean, there was great discussion going on out there. And that's the kind of discussion that we should be hearing from our students. The other thing that Laura and I did, a couple of things. One was on this chart right here. ADI has something different there. They have, what is your driving question? Is that right, Laura? What is your driving question? Dr. Brown, would you like to comment on that?
I don't know much about driving questions. I just know that the social studies people at my university, when they have them writing social studies lesson plans, that is something they require. What is your driving question? So it may have originated with the social studies people, because we do not use that terminology in math.
This is what we use in science. You go and look at any of the posters out there of our research scientists, you don't see a driving question, you may see a research question. They may not title it a research question, but if you look for it, and typically you'll see it out there. So that was one thing that Laura changed, was a scientific research question, not a driving question. There's also been questions about predictions, having students make predictions. That term is not found in scientific literature. What you will find is a hypothesis that they might be testing. So what's the difference between a hypothesis and a prediction? Well, it may just be semantics. It may be easier for your children to understand what a prediction is, and I don't see any problem with using that, but I think ultimately they need to be moved to the scientific language that a prediction is not exactly what we call it in science. Scientists call this a hypothesis that they test. So it would be like testing your prediction, what evidence do you find that supports that position or that prediction or hypothesis. And you do not prove anything. You may have evidence that supports it or not supports your hypothesis or prediction, but you don't prove anything. So you want to make sure that the kind of language that we have in the scientific community is the same kind of language that should occur in the science classroom, and that it should not be some other discipline's language, like driving questions, if that's from social studies indeed. We don't have driving questions in science, we have research questions. So that was one of the things that we changed. And Laura, you want to?
One of the things I wanted to clarify or bring up is that in our investigation, we didn't have a hypothesis. You weren't asked to make a hypothesis. You had a question, a scientific research question that you developed a procedure for coming up with evidence to answer that question. So whenever you did that, there was some confusion, I think, that if you came up with a hypothesis, that had to be your claim. And can you change your hypothesis? Well, yes, you can change your hypothesis, I suppose, or, you know, you can support or disprove it, or not support it. But your claim was this, that the liquids went into their layers because of their relative densities, that the more dense stuff went to the bottom, the less dense stuff went to the top. It wasn't I think that these layers will be like this, and then you gathered data. So if you predicted the order of those substances, and then you gathered data, did that prediction at the first make any, I mean, does it matter? I mean, you have to gather
Did
data
you have
to be able to
evidence
make
that
your
supported
prediction.
your initial hypothesis? If it did not
Yeah.
layer, as you quote predicted, or you hypothesized, then your evidence did not support your hypothesis. At that point, then scientists would change the hypothesis
Mhm.
based on their previous data.
But then this argument session that we had out here with our posters was not about your hypothesis and did your evidence support your hypothesis. This was kind of the analysis section of a lab report, I guess you could look at it, that here's what you were, this is the claim you can make, that it was about the densities, not about whether you supported your hypothesis or not with the layers of the liquids. Yes.
Excuse me, let me clarify that language. You don't support a hypothesis, the evidence either supports it or does not support it. It's not you supporting the hypothesis.
So on here it says the claim is your answers. I would think the claim is more like the conclusion, you know, to your data and your experiment then rather than your hypothesis. Like, your hypothesis is not your claim because your hypothesis could be rejected, but the claim is your answer.
I would put the claim as your hypothesis. That's what I think it's doing. And then your evidence would be your data that you collect, and our justification of the evidence would be, would have to be your conclusion. So I think maybe at some point, not right now, that we need to go back, because you're gonna see this a lot. This is the latest fad, okay? You're gonna see this a lot. So I think that we need to think about, you know, what is this chart? How can this chart be clear enough so that you can use it with children, or so we understand it well enough we can use it with children? Because I think they're saying some things that are a little bit different from what we see in the scientific literature. The other thing that Laura and I had a discussion about is in K-5, the children are supposed to learn about relative density. So relative density versus calculated density, that if we're going to have a triple beam balance listed here, then it seems to me like we're moving from relative density, which is just heavier or lighter, so to speak, to a calculated density. So is this mixing up a couple of concepts in here? So we're going to come back to it. This is not the only conversation that we have to it. I've got you, Elizabeth. Give me a minute here. And then there was a question about precision of accuracy with your instrument. So it was not accuracy that you were looking at. It was how precise could your instrument measure. You know, could it measure to a 1 mil or a 10 mil, or, you know, how many milliliters could that instrument measure? How precisely can it measure? So that was kind of, I heard some mixed language in there about, is this accuracy or is this precision? Elizabeth?
Oh, I was kind of citing along with Craig because I was taught, and I taught it, maybe I don't know if I taught it wrong, but claim was always at the end of whatever we did as a conclusion. Even if it was, and even if we're addressing questions, test questions, and I wanted them to write, and we called it a CER. And so claim would be the answer, and evidence would be whatever proves, she said it should justify what it was, supportive information instead. And then the reasoning was what you know about that question. And so in this case, after we made a prediction before we calculated it because we just wanted to as our own. They didn't say or not to. but if we had done it in a normal, investigation, then it would have been, your hypothesis is, we're just saying, okay, well, alcohol is gonna be there and, you know, syrup there. And then after we gathered all our information and did our calculations, then we made the claim from that, based on the evidence of our data table. And then the reasoning is what we know about density, less dense, more dense, and so forth.
Okay.
Is that,
I have one more thing.
Yeah.
Like, and also it says evidence to support your claim, so how do you get evidence to support your claim unless you know, did the actual experiment? You like, the claim comes after the evidence.
I know exactly what you're saying, and that's the way I took it too, that the claim was the answer to the question. And I think it, like, if you, it depends on how you wrote your hypothesis. I think that if you wrote it, I think that these liquids will be in this order from top to bottom. That's different than, I think the liquids will layer according to their relative densities from least dense to most dense, which allows for you to then go investigate what those densities are to then do your density column. So did that, yeah. But I agree that, I mean, that with the CER method, that, you know, the claim, when you're writing, you make your claim, you provide your evidence, and then you do your reasoning, which is how your evidence supports your claim, the scientific reasoning behind that. It is very similar to this. This just puts it kind of, I mean, I feel it in just a more graphical poster, simplified form, which you could then use to go back and write your data out.
I try to use this claim and evidence as an analogy would be for a gold mine. Before you can dig for the gold, you have to make your claim, saying that I think there's gold there. So you go make your claim. And now you have to dig and get your evidence. And then you can justify using your evidence about your claim. That's how I see it.
Okay. So
The most
if you
simplest
dug
is
and you
gold.
did not find gold,
Then it did not, your claim does not justify because you didn't find gold.
so how would you write up your reasoning then, or
That as I
your
dug
justification?
in my area or within my specific area, there was no gold there. So there's no evidence of gold.
So if there was no evidence of gold, does that mean that there was no gold there? I mean, what did you do to find out to determine that your evidence of gold or no gold?
I dug and couldn't find it.
So what if you didn't, sorry, go on, what if you just didn't dig deep
Deep
enough?
enough, that's what I was thinking.
Then, I mean, doesn't mean it's not there, or yeah, I mean,
Well, within
pockets
your
or.
parameters, you know, what you dug.
Well, let's come back to this again, because as I said, this is the latest fad. I have a problem with it in case you didn't, I mean, I think they're renaming things that we already have, and they're not using scientific
Right.
vocabulary, and it's confusing to people. But anyway, we're gonna come back to it, because you're gonna see it. I've been through part of the training. I've been through not 2 days. I went through about 6 hours worth, so not all of it.
And you walked out.
No, I didn't walk out. No, I would never do that. I want to understand it better. I'm at that point that I want to understand it better. I want to end this conversation because Dr. Browning's going to get started with some math, with something, a question and then comment. Did you have a control? No, you did not have a control, so it is not called an experiment because you did not have a control. So what's a general term for all the 3 types of research designs? It's an investigation, not an experiment. Because if you start calling things experiments, you're going to have kids and people and teachers looking for controls like I used to when I was doing labs with my students in high school, and they'd be doing something and they'd say, well, where's the control? And I'd say, oh, it must be there. I don't know. Now we do,
Dr. West,
yes.
is another way to think about it is experiments determine causation, why
Yes.
something happens.
Right, and you used the term why out there, and I didn't say anything at that point, but now I will. We don't often know why patterns in nature occur. We know when they occur, where they occur, how often they occur, we know lots of stuff about them, but we often do not know why because we cannot set up an investigation with a control. You can have a cause and effect with both a correlational and an experimental design. Because you will have a correlation coefficient that you can calculate to see what the strength of the relationship is. And we'll come back to that a lot more later on. Dr. Browning?
Okay. So, because we've been talking a little bit about things like this, then we kind of need to just review just a bit about ratios. This is going to be really simple. It's going to take me about 5 minutes. So while y'all were out at your gallery walk, there were some color tiles that were put on your workstation. So I want you, these are circles, but just pretend they're squares. So I want you to create this pattern of things. You don't have to use the red and the blue, as long as you have 2 different colors. That'll work. Okay. It doesn't say to determine that. Okay. So you should have 3 of one color and 2 of another color in a linear pattern. Okay? So they should be lined up. All right? So we're not going to do what this says. We're just going to talk about it. So what would be the ratio of red to blue? Red to blue? Or what? The 3 color to the 2 color. 3 to 2. And how, my question is that a fraction?
Yes.
3 to 2 is a fraction. Okay, let's talk about this.
Oh, no.
Hang on. I can't listen to all of you at one time, and I've told y'all before, I'm extremely old. So if you're talking when someone else is talking, I truly cannot hear you, okay? That's a lie, I really can't. But I want y'all to not talk while the other one's talking, okay? So the ratio here, I'm gonna use these colors up here. The ratio of red to blue is 3 to 2. My question was, is that a fraction? Raise your hand if you think it is a fraction. I heard some of you say yes.
Yes, but none of us are gonna raise our hand until.
Okay, raise your hand if you think it's not a fraction. Okay, raise your hand if you're not sure. Okay, so let's look at this. When you have a fraction, it's usually, and I'm not going to use your little green thing, I might put somebody's eye out. It's usually a part to a whole. That's the definition of a fraction, a part to a whole. So if we're comparing the red to the blue here, the red is a part, the blue is a part of that pattern. So this is a part to a part. Is that a fraction? Yes? No? Still not sure? Okay. That is not a fraction, because a fraction has to be a part of a whole. So many times I hear teachers say, this is a fraction, when really they mean this is a ratio. Okay? Let me see if I have anything else here. So what if I wanted the ratio of the red circles to the total number of circles? What would that ratio be? Quinn? Quinn?
3 out of 5.
3 out of 5, 3 to 5, that is the ratio. Is that ratio also a fraction?
Yes.
Yes. Can you tell me why, Kim?
Because all of it together is a whole. But the 2 colors themselves are parts.
Yes. So we're comparing the 3 to the 5. So is one of those a whole?
The 5 is the whole.
5 is the whole. Well said, see? No tears. So it's part to whole, that is a fraction, okay? That is a fraction. So, rates are when you have two different objects. So here you have bananas to a dollar bill. That would be a rate. Okay, how many bananas can I buy for $1? It looks like 4 bananas per dollar. That is a rate. Now, years ago, when I first started teaching way back in the 1900s, the textbooks made a big deal about is it a ratio or is it a rate? Is it a ratio or is it a rate? Nowadays, all the research I read, they don't kind of make such a big deal out of it. The only people that still do are the textbooks. But you do need to use the correct term. If it's two different quantities, it's called a rate. If they're the same quantity, it's called a ratio. So would we write a ratio or a rate for these two? Are you science?
Yes,
Okay, tell me the answer.
rate,
That's a rate. Why do you think it's a rate?
because those are 2 different shapes.
Two different shapes, so it's a rate. You all agree? Disagree? What if I just called them polygons?
Yeah, they're just little shapes.
Okay, switch my word, because circles are not polygons, so I can't call them that. Tim was gonna jump all over me.
He did, he went.
Yeah. And I thought it as soon as I said it, but shapes.
They're both shapes.
So they're both shapes. If we consider these just both shapes, could that then be considered a ratio?
Yeah,
Yes, so here's my question. Rate or ratio?
Rate
Rate.
What is this M for? What is rate?
Mass.
Mass, what is that?
Volume.
Volume? Is this a rate or a ratio? It is a rate. Can you tell me why? I need a science person. Are you science? Okay, you'll be science right now.
Is it because it's grams per milliliter?
Very good. She said grams here, that's the unit, right? Milliliters here, two different substances, grams and milliliters, even though there is kind of a connection, but two different substances, so this is a rate, okay? This is a rate. So, this is how you can say a ratio, 1 to 2, 1 to 2, or 1 to 2, or as Quentin says, 1 out of 2. That'll work. Would 1 out of 2 work for a ratio that's part to part?
No.
That's part to part. Let me back up. Could I say, let me get to the easier one. Could I say that the ratio of red to blue is 3 to 2? 3 to 2. That's appropriate language. All right. Could I say that the ratio of red to blue is 3 out of 2?
No.
No. So when you use that out of, it has to be a whole, out of a whole. Okay, so that's going to be a ratio that is also a fraction. Okay, so fractions are ratios, but not all ratios are fractions. Right? Okay. So I had one more thought. Let me, I don't think y'all can get this break, by the way, but I do have one more thought. You're talking about relative density here. We have the term relative in math as well. Does anybody, you math teachers, have an instance where you use the term relative? This is extra, by the way, and I won't charge you for it. Probably not something that pops up in your mind all the time. Okay, but that's that. What about relatively prime? What does that mean? Relatively prime. Think about it for a minute. Or 3 seconds, like Sandra says. Relatively prime. If you're a math person, I don't want you to answer. So a science person, what do you think that means, knowing what you know about relative density? Elizabeth, you can't answer all the questions. Ashley, are you science?
Yes,
What do you think?
yes. I'm going to be math, so better.
Your science today.
It could be maybe like a set of prime numbers put in a certain order.
Pretty close.
Because like relative density, it's like less to more.
Pretty close, not exactly, not exactly. So, you know, that dictionary for math science is coming into play now, because we have two different meanings for this word. Any ideas? Who are my math and science people in here? Okay, Crystal, you got an answer?
I was gonna say, since relative density is approximation, I was gonna say that maybe relative prime is a prime number within a common idea of numbers, a common range, like it wouldn't go too far. That was, it would be more common, like common set of numbers.
You're pretty close. You're pretty close. Anybody else wanna, what do we want? Do we want to make a claim or a hypothesis or a prediction here? A hypothesis?
Prediction. No, these tests.
Okay, a math person, what is relatively prime? It's not something you use all the time, so you may not have, it's not in the sheets, by the way. So you may not, if you're not my age, have taught it.
I can't guess.
Mhm.
It's like a number that can't be divided by another number, like.
Okay, now that's prime, so let's list the prime numbers. What's the first prime number? Jen?
30 and 11.
2. The next prime number, Melissa.
Like,
3.
Next prime number, Brenda. 5. Next prime number, who's next? I'm sorry, I haven't learned your name yet. Amanda.
Is it 7?
7, that was a question or a statement?
7. It's a
Thank
statement.
you.
well,
Next prime
I meant by
number.
each other, like.
I know, I'm getting to you. Crystal. 11. Next prime number, this is my last one, Quentin. 13. All of these are prime. Why are these prime?
They're only divided.
One at a time, raise your hand. Or I'll just call on somebody, Tanya.
Eye contact.
You stay
I
there.
try to pay attention to you, but I don't want to look at you.
Thank you. Did you call on me? I'm trying.
They are prime because they can only be divided by one in themselves.
One in themselves. They have 2 factors. They have 2 distinct. How do you spell distinct?
T-I-N-C-T.
I-N-C-T. See, my old brain kind of kicks in. Factors. So if they have more than 2 factors, then they're called what? Oh, I did it. What are they called when they have more than 2 factors? See, I ended my question with a what, which is an extremely bad thing to do. And then I caught myself. So I had to rephrase, okay? So, what are the numbers called that are not prime?
Unprime.
That would be me, out of my prime.
Composite.
Composite. So what is the definition of composite? Raise your hand, please.
Do you want a math person?
It doesn't matter at this point, Rochelle.
A number with 2 or more factors.
2 or more?
More than 2.
3.
3 or more? So more than 2 factors. Okay. So, if I have this fraction, 3 over, I can't even think of one right now.
10.
10, thank you. 3 over 10. 3 over 10. What are the factors of 3? 1 and 3. What are the factors of 10? 1, 2, 5, and 10. Do they share any factors? Other than 1?
No.
These are relatively prime. Even though 10 is composite, these are relatively prime. So, can you give me a working definition for relatively prime? And I'm looking at Tanya, and I'm not gonna call on her. Toby.
Relatively prime are numbers or can you call it a fraction at this point?
This is a fraction at this point.
This is a fraction that may consist of prime and composite numbers.
Maybe,
Possibly.
maybe, possibly. You want to refine that?
Two numbers in comparison with one another who don't share any common factors besides one.
Well said. No common fraction. Factors. No common
Oh, okay.
factors.
Except one.
One is common in everything, so you really, it's understood. So are all simplified fractions relatively prime? That is a great question. Why don't you talk to your partners for about 30 or 5 seconds, and then we'll discuss it.
30 or 5?
35.
30 or 5?
I really want to know.
1 o'clock this morning, drive on here, I'm tired.
What clicked in your head to make you say that?
Tanya, would you repeat the question? Let's be quiet. Tanya's gonna repeat the question.
So I said, so does that mean that all simplified fractions are relatively prime?
Okay, so that's what you're discussing.
Yes.
Math people, you're discussing, you're not answering.
So that would be a high relatively fast. Simplifying. Probably the relatively
Make this relatively prime.
I like that term.
So the verb for making it relatively prime is simplified.
Understood.
The verb for making it relatively prime is simplified.
Simplified, it's not, we're talking about the proper.
You're not taking anything.
So you're right.
Or the math teachers don't have to say
Thank you. Okay, so I need a non-math person to answer Tanya's question. So,
You could say aside from one.
Jen, I need a non-math person to answer Tanya's question. So, let me see. Melissa, you're math and science.
She wants science, it's only math a year.
Only science now. Okay, Candace, you're science. So, can you answer Tanya's questions?
I would say yes.
Guess what?
Yes, that simplified fractions are relatively prime.
Okay, so the numerator and the denominator of a simplified fraction, completely simplified, they are relatively prime. Can you tell me why?
2 fourths. No, it's 1 half.
Because
3 seconds.
There are no common factors, so if the fraction is simplified, then there would be no common factors.
very well said. So a fraction that is simplified completely, the numerator and denominator are relatively prime because they share no common factors. You brought up a good point. Let me back up to my bananas. He said, is this a unit rate?
Yes, because it's 2 1.
Think about it, is it a unit rate? To know that, to answer that, you have to know what a unit rate is, right? So, Mary Lou, do you know what a unit rate is? Your science, right? No, oh, good, your math. So what is a unit rate?
Per one,
What per one?
quantity of something per one of that, another quantity.
Okay, well said. The quantity of something per one of another quantity. So is this actually a unit rate? Good point. I hadn't thought about that. I just put this up here. I could have put $4 up there and then it would not have been a unit rate. But good catch. Thank you. And that's it. So I don't know if you're getting this right or not. That's a Laura question.
Yes.
Well, we've got some language issues here.
Okay. I'm gonna back up and leave it on that slide while you do your language issues. Okay.
Okay, we've talked a little bit earlier, or we mentioned it, about the language issues and the synonym versus, so synonym, a word having the same or nearly the same meaning, and there's a dictionary that we are working with to develop that. Homonym, so it's pronounced the same, but it has different meanings. The example is the generic one, bear in the woods versus, you know, you are bearing a heavy load, so to speak. So we have solve versus calculate, and there are some other ones that are going to come up whenever, okay, thank you. I know how to use this one too. Okay. That are going to come up with our discussions with this. So here are a couple of ones. This regular shape came up in a discussion. I was actually observing a lesson in Wimberley, a 7th grade lesson, and I was with another math instructor, and it was a density lesson, as a matter of fact. And they were using gummy bears to calculate density with, and the teacher was having them do a length by width, and I'm thinking, how do you do a length by width with a gummy bear? Doesn't that take calculus or something to figure all that out anyway? And I said, well, to the math person, I said, well, in science, we don't use, we only use a formula with a regular shaped object. With a irregular shaped object, we use water displacement method, yada, yada, you know that. And she looked at me funny and she said, a regular shaped object? What's a regular shaped object? Don't you know what a regular shaped object is? It's one that you have a formula with, you know, length times width times height or something. So anyway, this the idea of a regular shape is something that we use in science, but we don't hear that language in math. But Dr. Browning has got something to say about it.
Yeah, because I just want to clarify, in mathematics, we do have regular shapes and they don't have to have a formula, right? It's not based on having a formula or not. So if we have a regular polygon, any kind of polygon, what does that mean? I need a math person to answer. Pam.
All the sides are congruent.
All the sides are congruent and all the angles are
We
congruent.
talked about that last time.
Yes, so that was last summer. We did geometry all last summer. So the, you know, the old people, the returning people, I'm the old person. The returning people.
Experienced.
Okay. Okay.
Veterans.
Seasoned, all right. They should remember this, that if it's a regular polygon, all the sides are congruent, all the angles are congruent. Give me an example of a regular quadrilateral. Okay, I'll go back to Pam.
A square.
A square. So is a rectangle regular in math? Why not, Rochelle?
Because these sides are different.